Yes, students. Now, um, the result which was discussed in the result which was discussed in the previous session, we shall write it. We can express in a different way. That is, the previous session we discussed if a subset E of a metric space M, suppose E is a subset of M, where M is a metric space, and the point X is a limit point. The point is a limit point of E if and only if every open ball with center at X of this type contains at least one point of E. Suppose this is the metric space M, and suppose this is the subset E. We say that this X, suppose this is X, I say this X is it's not D, is a limit point. There may be many limit points for the same set. Suppose I say this is a limit point. So what's the meaning is, whatever open ball we construct with center at X, any open ball, but center is same, that radius alone will be changing. Something like concentric circles, you can imagine like this. Whatever open ball we consider, suppose one open ball, it is like this, with center at X, radius is R. This should contain at least one point of E. This element should belong to E. Okay. So like this. So any open ball we draw about that point X will contain minimum one point. It's not restriction that exactly one point. Minimum one point must be there. If there at least one open ball about the center X contains no point of E, then that point is not a limit point. So this is the result we discussed in the previous session. So what you can write this statement in a different way. So this also can be questioned in the examination. The question will be like this also. The point X in M is the limit point is a limit point of the set E if and only if there are points of E that are arbitrarily close to X. Arbitrarily close to X. That's suppose X is there here. If I say X is the limit point of this set E, so what happens is there are many points very close to E, but it's not equal to E. They are coming very close to E, but all these points will be belonging to E. So this is the another way of stating the result. So previously we proved it. X is a limit point if and only if every open ball about X will contain at least one point. This is the another way of expressing the same statement. That is, if X is a limit point, if and only if there are points of E that are arbitrarily close to X. If this is happening only, whatever open ball we construct about A, suppose about X, will contain at least one element of E. So this is the alternative way. This also this is the how to say alternative statement for this step. So both of the statements, the proof is same. Already we discussed. Now little bit intuition knowledge we are going to use it, and see we are going to go to some small results. Suppose E is a subset of plane R square. This is one x-axis, this is y-axis, this is R square. Suppose R square we take a plane, we call it as a plane. Then x is a limit point of E if and only if inside every circle about x there is a point of E. So what we can, how can you say that a limit point in plane? Suppose this is a plane and I say that this is the limit point of a set. So what happens is, you just construct an open ball, it will be like this. And E is a set. Suppose E is a subset of this R square. You think like this. So to be more clear, suppose you just take this is full plane. Suppose I take one set E. Suppose this is a set E. I say that this is in plane, two-dimensional. Suppose I say x. X is a limit point of E. So what's the meaning is, so what is the open ball in 2 dimensions? It's a circle. So whatever circle we construct with center at whatever circle we consider with the center at x, it should contain some points of E. If this happens, then we say that x is the limit point of the set. Just we are just imagining that it is in 2 dimensions. 2 dimension. This is x-axis and this is y-axis. Suppose L is a straight line. Suppose you take a straight line. And suppose L is a set. L is a straight line. Straight line in R square. Same thing. Something like this. This is x-axis, y-axis. This is a line. This is suppose L. L is a set. I name this set line means just a line segment you can take like this. It has some definite boundary. Okay, it's a line segment. So for this set, it contains all its limit points on the same line, because if I say that this is the limit point of the set, I can definitely construct one circle which contain no points of this L. So what happens is, for this structure, this is L in R square, all the limit points are inside the same set like this. If the limit point is there, it will be on the same line only. So that is what you can understand from here. This is by intuition. By just seeing it, we see that we see that there exists no limit point outside this line. So this is what you can see. Similarly, in 3 dimensions, R cube, L is a straight line in R square and a plane. You can consider a plane in R cube. Consider a plane which is a subset of R cube. Suppose 3 dimensions. Suppose this is a plane. And there exists no limit point outside this plane. So you can see, if you construct, if you say that this is a limit point of this set, in 3 dimensions, an open ball is it's like a sphere with center at this point. So definitely I can find one sphere with center at this point which is not containing any point of the plane. That is possible. So what you can understand is, in this plane, all the limit points will be on the plane itself. That is what we can see from here. So these are the simple examples they give. Plane in R cube has its own limit points. Similarly, straight line R square contains all its limit points. So what you can tell for any set E, for any set E we defined another set called closure of the set. That is, this contains all the limit points of the set E. Already we proved that always E is a subset of E bar. So very rare cases the closure of the set will be a subset of E. If this happens for any set, then we can say that E equals to the closure. If this is satisfied, we say that the set is a closed set. So what you can come to conclusion is, in R cube, every plane is a closed set, and in R square every straight line is a closed set. So this is for this purpose only they have explained these things. So now another one, these things you can just something like remarks. These are the small results. You can make a note. So suppose you consider a metric space. N is a metric space. With some metric is defined on it. And suppose I say X is element of M. Then for any metric space we say that X is a closed subset of M. Why it is closed? Because in any metric space singleton sets are closed. So why it is closed we are going to see. Because when you say a set is closed set, just now we explained, the set E is closed if it contains all its limit points. No limit points is outside the set. So now you take this set X, the only sequence that is present for this set is what? The only sequence of points, is this set. This is the only sequence available in this singleton set and converges, and this only sequence also what happens is converges to X, and this X would already belonging to what? X. Therefore singleton sets is a closed set. So what you can come to the conclusion, in any metric space, whether it is real line or RD or everything, singleton sets are always closed. If they ask the proof, this is the proof. Why singleton sets are closed? Because the only sequence available in a singleton set is, suppose X is X, X, and definitely this sequence converges to a real number, converges to a point X, but this X is already in X, the singleton set. So the only sequence, the limit point, which is X, is inside the singleton set itself. So in any metric space, singleton sets are closed. So this is one small result. And now what about RD? In discrete metric space, already we proved every singleton element is open. So already we proved it in open sets. In the topic open sets, every subset of RD is open. We have proved it. And every singleton set is an open set. In RD, every every singleton set, say A, is open, and also we have proved one result, and every subset you take, every subset of RD is also what? Is closed. Already we discussed these results. Now we come to give some information regarding the closedness of this discrete metric space. So what happens is, just now we proved that in any metric space singleton sets are closed, but only in RD we already proved that singleton sets are open. Therefore, if we combine both of them, what we get? So therefore, in discrete metric space, the singleton sets A, suppose A, singleton sets are both open and closed. Both open and closed. It's not for all the metric space, only for RD this is possible. So what the author says is, if suppose a room is there, if a door is available, then either the door is either closed or open, only that is possible. But for RD we can see that the set is both open as well as closed. So sets are not like doors, because doors are usually either closed manner or open. So you can see here in RD the sets are both open as well as closed. So the author is giving some things that is relating some doors and these open sets and closed sets. Okay. So we cannot come to the conclusion that always a set will be closed, always it is open, not like this. For some metric spaces a set is both open and closed. Example is RD. In RD every singleton set is both open as well as closed, but in any general metric space singleton sets are closed. But there are some examples of sets which are neither open nor closed. That is also there. For example, we consider one half open interval 0, 1. Suppose we consider R, the usual metric. Here A is neither open nor closed in the given metric space. Why it is neither open nor closed? Because you see this set 0 is included and 1 is excluded. So all these points we consider. So this is our A. This set is not open because the entire real line we consider as the metric space plus infinity, and the entire real line is the metric space. So what is the definition of open set you have to see? What is an open set? A set is said to be open if whatever element we take, there must be we can construct an open ball such that it is completely inside. So now you construct an open ball, 0 is a point inside A. So you construct an open ball about 0. An open ball in one dimension, that is 1 R, is what? An interval. So it will be like this. So what about these points? This is in R, but it is not inside A. So I constructed an open ball, that is an open interval, only this part of this open interval is inside this set A, but what about this part? It is not inside A. So it is not obeying the law of open sets. So this set is not open. I given only one, I took one element, I disproved that. So now why it is not closed? Why it is not closed? So because we take one sequence in this, we take one sequence that is which comes very close to so 1 by n, no, not 1 by n. So what about the sequence 1 minus 1 by n? Just consider the sequence. What happens? You see this sequence. What happens with the sequence? So the first element is 0. I'm just considering this set A. I'm considering one sequence inside this set A. What is that sequence? This is 1 minus 1 by n. What is the second element? 1 minus 1 by 2. That is 1 by 2 somewhere here. Next 1 minus 1 by 3. 4 by 3. So somewhere here. But, sorry, not 4 by 3. Sorry. 3 minus 1, 2 by 3. Somewhere here. 2 by 3 means 0.666, so it's greater than, okay. Next 1 minus 1 by 4. 4 minus 1, 3 by 4. It is what? Something like this. 0.75 like this. So what happens is, when n tends to infinity, what happens? This sequence comes very close. When n tends to infinity, what will happen to this sequence? It converges to 1. But this sequence converges to a point 1, but this 1 is not inside its set A. So we found out one sequence in A converging to one number, but this number does not belong to A. So the limit point, this is the limit point. This is the limit point of the set A, but if this limit point should be inside A, then only I can say it is a closed set. This is true for any sequence you take. So I given one example of a sequence for which the sequence is inside A, but the limit is not inside A. So the limit point is not inside A. Therefore, that is the reason this set is not closed. That is the reason the set is not closed. Already I explained why it is not open. So you can make a note. This set 0, 1 inside R is neither closed nor open. RD, every singleton set is both open, closed. So these are the examples you have to keep it in